Hello friends, in continuation with the last lecture, we will try to find out the eigenvalues of the angular momentum operator. So what we have seen in the last lecture is nothing but the L square commutes with the L bar, means the each component of the angular momentum is commuting with the square of its angular momentum, okay, is equal to the 0. So here the L square is the compatible with each component of the angular momentum, and we can hope to find the simultaneous eigenstates of the L square, and say one of the component as of the angular momentum as a LZ. Okay, and we'll see in a moment that the why we have chosen that the LZ component, why not the LX and LY. Okay, so what we can have, they will be having the simultaneous eigenstates for it. So when L square operates on the some test function f, then what will get the eigenvalue is lambda and the test function itself. Similarly, what we can have the LZ when operates on the test function f, then we will get the another kind of the eigenvalue as the mu into f. So now we will use the ladder operators, just we have seen in case of the angular in the simple harmonic oscillators. Okay, so now how to rewrite the ladder operator for the angular momentum, or the that is nothing but the L bar L plus or minus is defined to be the Lx plus or minus ILy. This is the definition of the ladder operator in case of the angular momentum. So its commutator with the Lz is given as, okay, so let's see. Now see here, it is the Lx and Ly. L plus and L minus is composed of the x component of the angular momentum and the y component of the angular momentum. Let's try to find out the commutator bracket of the Lz with L plus or L minus. Okay, so Lz is nothing but Lz commuting with the commutator with the Lx plus or minus ILy. So let's try to rewrite this equation in the simpler form. Just simplify it, and what we can have, what is the Lz commuting with the Lx, that is cyclic one, so we will get the IH cross Ly, and here we will get the minus IH cross Lx. So just try to substitute over here, so IH cross Ly plus or minus I into minus IH cross Lx. So if you just try to take out the plus minus H cross out of it, and then what we will get, Lx plus or minus IL y is remaining one. So this is nothing but the our usual ladder operator which is defined over here. Okay, so that is nothing but the L plus or minus Lz commuting with the L plus minus is nothing but plus minus H cross into L plus minus itself. So, and let's, of course, what we can have, the L square is commuting with the L plus or minus, because as we have seen that the L square commutes with the L bar, each component of the angular momentum. So L square also commuting with the ladder operator one. So that gives us the 0. Okay, if suppose now f is an eigenfunction of the L square and Lz, so also for the L plus minus f as well. Okay, L plus or minus. So this is also for the operator, we will be having this as a eigenfunction. Therefore, what we can have, the L square which is going to get operated on the L plus or minus f. Okay, this is the eigenfunction for it. So, or else what we can have from this equation, what we can get, it nothing but the L square, L plus or minus is equal to L plus or minus L square, because they are commuting with each other. So this is defined to be the L plus or minus. When L square operate on the f, will get the lambda as its eigenvalue. So L plus or minus lambda into f. So lambda is a eigenvalue, so it is constant one, it can come out of it, and the L plus or minus. So this is the L plus or minus into f is acting as an eigenfunction over here. So this is eigenfunction of the L square with the same eigenvalue as a lambda, which we have defined earlier as well. Okay, now here, when just similar eigenfunction we will use here, and that is L plus or minus, and what we can have, Lz going to get operate on this L plus or minus f is nothing but the we can just define the rearrangement in this step, that is L plus or minus Z, plus and minus adjusted over here, so that this is defined to be the commutator bracket of the LZ and L plus or minus, which we have already seen in the previous few steps back. So this will give us nothing but the commutator bracket of the LZ. Okay, this is nothing but the LZ commutator bracket with the L plus or minus 1. Okay, so this is what we have seen it now. And here the L plus or minus LZ when it is operating, LZ is operating on the F, will give us the mu as its eigenvalue. So it is defined over here. Okay, so what we got it when LZ operated on the L plus or minus F, we got the value as a mu plus or minus H cross and to L plus minus F as well. So here L plus minus F is an eigenfunction of the LZ with the new eigenvalue as a mu plus or minus H cross. Okay, so this is eigenfunction we have chosen. So L plus is called as a raising operator, because here we can see the eigenvalue has been increased by the 1 or raised by the unit Planck's constant, okay, plus H cross, okay, plus H cross unit it has been used. So L plus is called as the raising operator, and it increases the eigenvalue of the LZ by H cross. Similarly, L minus is called as the lowering operator, because it lowers the eigenvalue by the H cross. Okay, it lowers the eigenvalue by the H cross. Okay, now here we'll see for a given value of the lambda. Okay, if we have chosen as the eigenvalue of the given value of the lambda, we obtain the ladder of the states with each rung separated from its neighbors by 1 unit of H cross in the eigenvalue of the LZ. Okay, what we have considered here, that is nothing but we have considered the one of the arbitrary state having the its eigenvalue as a mu H cross. Okay, or else we can have the eigenvalue as the lambda 1, and if we just try to operate the our raising and lowering operator, we can find out the each rung of that operator 1. Okay, so there exists now when we just try to operate the L plus operator on the each that arbitrary state, then we will be reaching at the top one. Okay, we will be reaching at the top rung, and above which there will not be single rung will be existing one. There will be single rung will be not existing. So this is what we can have. This is the arbitrary state having the its eigenvalue as a mu H cross, and when it is getting L plus is getting operated, what will be reaching one step with the each operation, and will reach 1 2 3 4, and here we will reach the top rung, and above which there is no rung is possible one. This is the topmost one. So what we can have, L plus is going to get operated on the eigenfunction as the top rung corresponding to it, and that will give us the 0, because there is no existence of the rung above it. So let that LH cross be the eigenvalue of the LZ at this top rung. So what is the eigenvalue we have considered? That is the LH cross for that top rung. So LZ operating on the FT will give us the LH cross into FT, and L square when it is going to get operated on the top rung will get the eigenvalue as the lambda into FT. Now let's try to operate the consider the product of the this raising and the lowering operator. So this upper sign corresponds to the upper sign for the this as well. Okay, so the another in this L plus this operator upper sign plus here and minus 1 is considered, and for another case we can have the when we consider the bottom sign, here also we need to consider the bottom sign. So the raising operator, the product of the raising operator and the lowering operator is considered here. So Lx plus IH cross Ly and Lx minus IH cross Ly. So this product we have considered here. So what it gives us, the Lx square plus Ly square minus plus I into Lx Ly minus Ly Lx. So this is nothing but the commutator bracket of the Lx into Ly, and that is nothing but the IH cross Lz. Okay, so that product is given as a IH cross Lz, and as we know that the Lx square plus Ly square, but we can define the L square operator as a L square is equal to Lx square plus Ly square plus Lz square, but we can rewrite this Lx square plus Ly square as a L square minus Lz square, because we know the eigenvalues corresponding to the Lz and L. So what we can have, Lx square plus Ly square is equal to L square minus Lz square. So what we can have here, L square minus Lz square is replaced for this Lx square plus Ly square, minus and plus I into IH cross Lz. So putting it in the another way around, so L square is nothing but the, so we can define the L square in terms of the this L plus minus operator, raising lowering operator, as well as the L square is written in terms of the raising lowering operator and the Lz operator in terms of the Lz operator one. So it follows, so here it follows that the L square, when operating on the Ft, okay, the top rung or top rung eigenfunction, that is nothing but the L minus L plus Lz square plus H cross Lz into Ft. So L square has been value has been replaced with this eigenfunction, or the new definition of the L square. So when the Ft, when now we will just try to operate this L plus L minus L plus operator on the Ft. When L plus operator on the top rung eigenfunction, we will get the 0 1. So that's why we will get the 0 1. So no need to operate this L minus operator on it, okay, because we have chosen to be, or else why we did not choose the L plus and L minus, because we will get the when L minus operated first and on the Ft, then we will get the some eigenvalues, arbitrary one, and then if L plus operator, then we will reaching to the top top rung, and will be getting the some another eigenvalue. So that makes a complicated one. So what we can have, we have chosen to be the L minus and L plus one operating on this Ft. So this will give us the 0. When Lz square operating on the Ft will give us the corresponding eigenvalue as a L square. When first it operated, you will get the one L and then the LH cross, and then the next time when you operated, then it becomes a square, and then again eigenvalue is a LH cross, and then the H cross into LZ eigenvalue is the LH cross square. So when L square is operated on the top rung, we'll get the L into L plus 1 H cross square Ft as its eigenvalue. And as we know that the we have considered initially that the L square operating on the Ft will give us the eigenvalue as the lambda. So what is the lambda value here? Hence we can write down the L is lambda is nothing but the L into L plus 1 H cross square. So what it tells us, that the eigenvalues of the L square in terms of the maximum eigenvalue of the Lz, okay, what it gives us, the maximum eigenvalue of the Lz, okay. So this is what corresponds to. Now meanwhile there is also a bottom rung. Obviously when we just try to operate the L minus lowering operator on the arbitrary rung, and we will be reaching to the bottom rung, that is defined to be here. So when if we just try to operate the L minus operator, obviously its eigenvalue each time will get reduced by the one unit of the H cross, and it will reach to the bottom rung, and the corresponding eigenfunction is defined to be the Fv, okay, and its eigenvalue as L bar H cross, okay, its eigenvalue is defined to be the L bar H cross. Let the L bar H cross be the eigenvalue of the Lz at this bottom rung. Now Lz operating on the bottom rung will give us the L bar H cross into Fv. Similarly, L square is operating on the bottom rung will give us the lambda at say eigenvalue Fp. Okay, this lambda is something is similarly as we have defined in the initial case. Okay, on the bottom rung we are just trying to operate. Now using equation for the L square. Okay, L square here. Now what we will choose? Now we will choose the product of the bottom. We are going to choose the L square operator such that the when L minus operating on the Fb will get, there is no existence of the bottom rung below the bottom rung. So what we can, will choose the L plus L minus operator here, plus Lz square minus H cross Lz into Fb. So here what we can have, L minus operating on the bottom rung will give us the 0 at its eigenvalue, then the Lz square, and no need to operate the L plus again, because 0 will give us the 0 again. So Lz square operating on the bottom rung will give us the eigenvalue as the L bar H cross square minus L bar into H cross square again, and the its eigenfunction as well. So what it gives us, the L bar into L bar minus 1 h cross square fb. Hence what is the lambda we got it? That is nothing but the lambda is equal to L bar into L bar minus 1 h cross square, or h cross square into so on and so forth. So if we just try to compare this both the equation or the eigenvalues of the this lambda, because both are one and the same one. So what we can have, L into L plus 1 is equal to L bar into L bar minus 1, and here what we can have, either or it has to be the equal one, because L cannot be equal to the L bar, or else the L plus L cannot be equal to the L bar minus 1. So what we have chosen here, that is nothing but the L bar is equal to L plus 1, or because L and L bar can't be the same, so L bar is equal to L into L plus 1, or else what we can have, L bar is equal to minus L bar, sorry, L bar is equal to minus L. Why we have chosen this? The bottom rung here, if we just choose this as eigenvalue, then L bar is equal to L plus 1. So what is the, this is the topmost eigenvalue for the what we can have, the top rung. Okay, so this is the eigenvalue corresponding to the top rung, and we know that there is no existence of the rung above the top rung. So what we can have, bottom rung's eigenvalue cannot be higher than the top rung's value. So this is absurd one. So we can discard this solution. Okay, we are discarding this solution. We will be choosing this one. So L bar is equal to minus L. L bar is equal to minus L as its eigen value. Okay. Now, evidently, the eigenvalue of the LZ are mh cross, and which goes from the minus L to the plus L in the n integer steps. Okay, so it reaches in the n integer steps. So the eigenvalues are characterized by the numbers L and M. Okay, so here the eigenvalues are just characterized by the number N, L and M. So in particular, if you just follows the case something like, okay, I just rewrite that the L is equal to minus L plus N, and hence what we can write down, the L is equal to N by 2. So L must be an integer or a half integer. So L can be an integer or the half integer, and eigenfunctions are characterized by the values of the L and M. So L square, I just rewrite my eigenfunction as FLM. So L square operator on FLM is nothing but the L into L plus 1 h cross square FLM, the eigenfunction itself. So and LZ, when operating on the FLM, will give us the M h cross FLM as itself. So here the L value goes from the 0, half, 3 by 2, and so on and so forth. So and the M values will goes from the minus L to the plus L with the integer step, with the unit integer step. So for a given value of the L, there are 2L plus 1 different values of the M. That is 2L plus 1 rungs on the ladder are existing here. So rungs on the, so we hope here that you must be impressed with this by purely algebraic means, starting with the fundamental commutation relation, and we have determined the eigenvalues corresponding to the L square and the LZ. Okay, we have to, without seeing the eigenfunctions themselves, we haven't chosen, we have chosen here the eigenfunction as a arbitrary one. So we now turn to the problem constructing the eigenfunctions in the next lecture. So I should warn you that this is much messier business, but okay, let's talk about it in the next lecture.